Okay, back to finishing up this problem real quick. We already figured out the Q of the water using SM delta T. Then, because the water absorbed that much energy, then we know the reaction lost that much energy. But the next thing we need to do is, sorry, hold on, I'm getting ahead of myself. The Q of the reaction is simply the same thing as the delta H in this scenario because no work was done. No gases were formed. It was all at constant pressure. Now, the last step here is it wants to know the amount of energy released per mole of hydrochloric acid. So I went ahead and put it in kilojoules here because I believe that's what it asked for. So there's 1,000 joules and a kilojoules. And now we need to figure out how many moles of hydrochloric acid were used. So, oh no, we have to do a molarity problem again. Okay. We know that there was 500 milliliters or 0.05 liters of hydrochloric acid used, and it was 1 molar. So, because it's 1 molar, there's 1 mole of HCl per every liter. We didn't use a whole liter, we only used 0.05 liters, so that works out to be 0.05 moles of HCl. So now I take my delta H in kilojoules and divide it by my moles of HCl to get the kilojoules per mole. And it's 58 kilojoules per mole of HCl is the enthalpy of this reaction. All right, so in our calorimetry problem so far, if you refer to that handout I gave you that's just in my handwriting, it's a photocopied piece of notebook paper. It's got all the different kinds of calorimetry on there. There's type 1, which is just one object, so you just do Q-SMAT once. Then type 2 is the hot metal in the cold water. And there you set the negative SM delta T of the metal equal to the positive SM delta T of the water, and solve for whatever it is you're trying to figure out, but it's usually the specific heat of the metal. And then type 3 is aqueous chemical reactions. There you just Q-SMAT the water, change the sign, and then divide by the moles of whatever reactant you're told to use in the problem. Okay, so here is another one, very similar to the one we just did. I can work this one out in class because you probably need to see more than one of these before it makes sense. So the thing to remember with these, with type 2 and type 3, these are constant pressure calorimetry problems. Whatever heat is gained or lost by the reaction is equal to the heat gained or lost by the surroundings, which the surroundings are more than just the water. It's actually the water and the calorimeter. And when we do labs, we'll have to account for the little bit of heat that gets absorbed into the coffee cups. So the enthalpy change is equal to the Q of the reaction in constant pressure calorimetry because there's no work being done. And in reality, a little bit of the heat released by the reaction goes into the calorimeter cups, the styrofoam cups too. It's not just the Q of the water. So sometimes we'll just be simple about it and ignore that fact like we did in the last example. Other times we'll go ahead and correct for it. You'll just have to see one like that. Okay, now this is the last type. This is bomb calorimetry or constant volume calorimetry. Okay. Here we have the reaction carried out under constant volume instead of constant pressure. To do that, you need a piece of equipment that we don't have, and it's called a bomb calorimeter. The most common type of reaction to use for bomb calorimetry is fire, combustion reactions. We know, well, to do these, we'll have to know the heat capacity of the calorimeter. So C is heat capacity, and then they write cal after it for the heat capacity of the bomb cal. And then the heat of reaction. Okay, so mathematically, these are pretty simple. The Q of the reaction is simply whatever the heat capacity of the calorimeter is, which will be given to you in the problem, times the delta T. Pretty simple mathematically. All right, so because we're carrying this out under constant volume, the reaction's happening not in a styrofoam cup this time, but in a metal vessel called a bomb. It's a really thick steel vessel that cannot change volume. So if the volume can't change, then no work can be done. So once again, the change in energy is just the Q. So we get to ignore work. So this is what a bomb cal looks like. So to get The Q of the reaction will have to take into account the Q of the water and the Q of the bomb. What it is this. This is the bomb cal right here, that heavy metal vessel. And you have a sample cup usually made out of something non-reactive like platinum. And you put some gasoline or some TNT, whatever you want, anything combustible in here. And you run little electrodes to it. And then you fill the vessel. There's an oxygen inlet here. You fill it with oxygen because you need oxygen for combustion to occur. And you, of course, weigh the amount of TNT or gasoline, whatever it is you put in here. You need to know its mass. Then you put it in a bath of water. Quite a bit of water because these generate a lot of heat. And you've got a thermometer down in there and a stirrer, of course. And then you press a button and it ignites it. And this reaction happens and it releases a bunch of heat. It can't expand because of this thick steel container, so it doesn't do any work. So all the Q comes out of this reaction and it's used to raise the temperature of the bomb itself and all this water. And once you figure out the Q of the whole thing, that's the Q of your reaction, just the opposite sign. These will always be exothermic because they're combustion reactions, so you'll always have a negative Q. So the Q of the water plus the Q of the machine, and the vessel and everything, that's what equals the heat capacity of the calorimeter. The good news is in the lab, I had to figure this all out, figure out the heat capacity of the calorimeter and stuff. But for you guys, it'll be given to you in the problem. Okay, so here's an example so you can see how simple this is mathematically. We got a 0.5 gram sample of octane, C8H18. We put it in a bomb cal that has a heat capacity of 11.3 kilojoules per degree Celsius. So that means it takes 11.3 kilojoules of energy to raise the temp of the water and all the other parts of the calorimeter by just 1 degree Celsius. Then the octane is ignited in the presence of oxygen, of course, and the temp goes up 2.25 degrees. How much energy was released per mole of octane? Can't forget that part. So just try to understand what the question's asking you. You're burning something, it's releasing heat, and it's going to heat up the water and the machine by 2.25 degrees. So list out what you know. You know your mass of your octane, you know the heat capacity of the machine, and you know the delta T of the machine. Well, right here, even without a formula, you can see this is in kilojoules per Celsius. So if I multiply by Celsius, Celsius will cancel, and I'll have the kilojoules that were released. But we want kilojoules per mole, so we're going to have to take our grams of octane and convert it to moles. All right, so here's the equation. The Q of the reaction is simply the negative heat capacity of the calorimeter that was given in the problem times the delta T. So here's the heat capacity times the delta T. Celsius cancels, and we are left with just kilojoules, 25.4 kilojoules. The reason the negative's there is, remember, the Q of the reaction is always going to have an opposite sign as to that of the water and the calorimeter and everything. All right, so we want it per mole of octane now, so I've got to convert my grams of octane to moles of octane. So now, to get the enthalpy per mole, I just simply take the enthalpy and divide it by the moles. And here it is. This is a much larger delta H than we saw in the acid-base reaction a minute ago, which makes sense because this is fire. So the enthalpy of combustion, or energy of combustion, is negative 5510 kilojoules per mole. All right, here's another one regarding rocket fuel that we can do in class. All right, that's it for now on calorimetry.